equivalence point, or you got halfway to the equivalence point, so we call it the half equivalence point. And you can look at your numbers and say right away it must be what? 20 milliliters of titrant. For this problem, I could just be easy to say NaOH, but I'm saying in terms of titrant because, as I said, I can give you the problem either way. So I want to do that. I want to calculate the pH in there. So what I need to know, and this is why you know that this is why you're. Right? My zero I didn't put it quite at the right place. I think I put it in the right place. 1, 2, 3, 4. Darn. Oh, I know. So you put my. I think I started my zero here. I put my zero here, so my 0.7 should go here. I just plotted it. But I'm not going to ask you to plot it, I'm just going to ask you to calculate the pHs so you don't have to worry about all these fancy things. Notice when you read these problems in the book, he tells you to plot the titration curves and things. All I'm worried about is can you calculate it, because I'm not going to sit there and look at your graph. I just want to know the numbers. Okay. So coming back to this thing, I want to know what the pH is at that half equivalence point. And what that means is, I know I have excess HCl. Because anywhere along here, before I get to the equivalence point, I have a little bit of HCl left over. And the last couple of times we've been saying the thing with the highest K, largest value for K, is the thing that you use in your calculations. This is a strong acid, so that means the HCl must determine the pH. Okay. So I want to find out how much hydrogen ion I have left. And I've been saying this for a couple of lectures, or at least one lecture for sure. You always do stoichiometry first, followed by your equilibrium, or your whatever calculation you want to follow with. What's the stoichiometry going to be for this? Base plus acid. They're strong, so I don't have to do anything else with it, because that's the net ionic equation. Is water. And I know I started with 20 times 0.2. And since the volumes and concentrations are all different, you always have to work in moles. You can't subtract molarities unless you do the dilution problem for both reagents, and then you can subtract molarities, but it's better to work with these problems in moles. Or in this case, it's millimoles. And here I've added 20 milliliters of what?
NaOH.
This is 2 millimoles. This is what? 4 millimoles. There's my limiting reagent. You remember that term. I've used it a couple of times already. And so you go -2. And I did this thing last time. I'm going to just remind you, but I'm not going to do it anymore because I already said everything is always going to be 1 to 1. -2. There's nothing over here to worry about, so I'm not going to say anything because water doesn't do anything except sit there and slightly dissociate. But the important thing is there's 2 millimoles of hydrogen ion left over. And total volume is that's going to give me the concentration of hydrogen ion. And the pH. It's about 0.05 molar. pH is 1.3. I'd like to see more significant figures, but But since I don't have that much detail on my graph here, I can plot it. Let's see. That's 0.7. So this is 1.3 right in here. Notice the pH has hardly changed, and I'm adding the sodium hydroxide because the graph is going continuously from here to here. Okay. What should I do next? Oh, I'll do a couple extra calculations. I'm going to do 30 milliliters of nitrogen because I picked different volumes. And I usually use pretty significant figures. So I'm adding 30 milliliters of the titrant. Again, we have to do the same sort of thing. And notice if I do 30 times 0.1, I'm just going to write the answer this time, because you can do that. But if not, on your paper, do it. Okay. Over here, I don't have to do that multiplication anymore because I'm always talking about adding the 30 milliliters to this thing. When you're doing the titration, what you did was you added 20, and you measured the pH, and then you added another 10 milliliters and measured the pH, and you added another 10 milliliters. So basically I'm calculating as though I went from 0 to 30 directly. So I added 3 millimoles of hydroxide to my original 4 millimoles of acid. This is still a limiting reagent. And now I have 1 millimole of acid left over. It's still a strong acid HCl. And so I can say the concentration of H plus equals 1 millimole. Now my total volume has to be my original 20 milliliters, wherever it was, way over there is my original problem, plus the 30 milliliters of titrant that I added, which gives me 50 milliliters.
Dr. Danner, I can't read what's next to the concentration of the hydrogen at the top there.
Where are we?
What's in the numerator of that?
2.0.
It's 2.0 at the all the way.
We're up here?
Right there.
Yeah, is that 2.0?
Yep, let me go to the darker pens.
Thank you.
It's because there's a light that
Yeah.
shines right there.
There, that makes it
Now I
better.
can see it. Thank you.
Yeah, I was trying to conserve ink. Okay. So down here I have 1 millimole left. I'm dividing by 50. It says 0.02 molar. And I take my pH because that's the hydrogen ion. And I get 1.7. Notice the pH, as I'm adding the sodium hydroxide, barely changes. It has to eventually pass through that high point. And I wouldn't ask you to calculate something like 39.9 milliliters in this class. In quantitative analysis, I might. Why wouldn't I ask you in this class? Because you have to go through the thing we did with the 10 to the minus 8 molar HCl. We have to do a much more complex problem where we have to take into account hydrogen ion from both water and the weak, the strong acid and base, or base. So basically, I could ask you 39 milliliters. I'm not going to. I want to get to a better calculation. But here's how the curve goes. Okay. This part stays flat over here. But somewhere in here, right after you pass, I can probably get even closer to 39 milliliters before it starts doing this. happens if I add 41 milliliters of NaOH?
Excess. How did you?
Yeah. I'll do the calculation here.
So bring the pH back down.
There are two ways of thinking about this. Somebody just said, I have 1 extra milliliter of NaOH. I could do it that way, because if I know the volume of NaOH, that's not a strong base, that's what's going to determine the pH. Okay? Or I could do the thing I've been doing all along. Notice this is still my starting millimoles of HCl, which is still 4. But now I have 41 times 0.1 for the NaOH. Notice I like all these numbers, I can multiply them in my head. And you can see that the limiting reagent is now the H+. So you have 0.1 millimoles of hydroxide in excess. Okay? So now you can use this and say concentration of hydroxide ion, 0.1, over the total volume, which is 41 plus 20. 61. Notice the other thing you could have simply said was, you have 1 milliliter excess NaOH times the 0.1 molar for NaOH. What do you get here? 1 times 0.1 gives you 0.1, so you just calculate it directly from the excess volume of the NaOH. You get the same number either way, so it doesn't really matter which way you do it. Okay. So now we need, first of all, 0.1. Then we get 0.00244. I'm not going to write anymore because it's all here in my calculator. And I'm going to say I need POH is 2.6 because it's hydroxide, so I get POH. But I'm plotting pH, so I have to say that pH is 11.4. So I'm at 41 milliliters, which is right next to this line, and it's 11.4. There's my 11. Cross it. So it's right about here somewhere where I wrote my number. Oops, that's not what I said. POH. 2.6 is the POH, and 11.4 was the pH. And so you see the curve goes like this. And eventually you'll start going over as you add more and more excess NaOH. That's what your titration curve looks like for the titration you did. Now the phenolphthalein that we used for the indicator changes, it's colorless below pH 8 and turns red above pH 10. So they always do something like this. Here's 8 to 10. So right in here is where it changes color. And so you have a slight titration error. The endpoint isn't exactly the same as the equivalence point. The indicator should have changed right at pH 7, but it changes at a little bit higher. But notice this is so steep that there's only a small error.